So we're to section 3.6, a summary of curve sketching. After looking at all of these different things, where do we find relative? Talking about relative extrema, using the first and the second derivative test to determine where we're increasing, where we're decreasing, where we have our relative extrema, where we have our concavity, where's our end behaviors doing, putting us all together to sketch a curve. This section I basically have broken off into several videos because most of it is working example problems, and each of these problems take quite a bit of time. So instead of making one humongous long video, I'm going to make a few smaller ones. Each one do a couple examples so that you can kind of pick and choose what you want to do. But we're going to first work through one together, and then I'm going to give you a chance to try some yourself and then work you through these. So our main idea is to be able to analyze and sketch the graph of a function. So, and the thing is, with graphing calculators and computers, you can easily graph. We don't, back in the day, this was really important to get a good idea of the picture of a graph because I couldn't just go to decimals and type it in and get it. But it's still kind of important because, and we've talked about this before, the limits with technology is they're going to do it in whatever window they think they have it, and trying to sometimes knowing more of what's going on, some of these things we're going to find help us set the best window that we can get our best view of the graph and see what we want to find out on here. An example, if we take this function x cubed minus 25x squared plus 74x minus 20, if we graph it on this window, it looks like a parabola. And if we don't take some thought to say, hey, this can't be a parabola, we might just go along thinking it's a parabola, and that might get us into trouble. We know it's third degree, so we know somewhere it has to turn around. But again, is it going to turn around on the left, or is it going to turn around on the right? I don't know. If we change our window, we can see the full function. This is what we call a complete graph, and that gives us a better idea of what we're going. By finding out that, hey, I have a relative minimum here at 15, this looks like, about 1150, negative 1150. I wouldn't know that, but that gives me enough so I can draw this graph. So, the tools we have, and sometimes we use some of these, sometimes we don't necessarily use them all. But we can look for x-intercepts, y-intercepts, think about symmetry, things might help, domain and range, continuity, vertical asymptotes. These are all things we could do with pre-calculus ideas, most of these. But we get into calculus and we start looking at differentiability, finding where the relative extrema are, finding concavity, points of reflection, horizontal asymptotes, limits at infinity. Now these are some more things we can look at. These are all tools in our toolbox, and we use what we need. So pretty much your guidelines, start looking at the domain and range. Domain is especially, are there any vertical asymptotes? Range kind of gives us an idea of how big the graph wants to do. Range also might be, no, not necessarily end behavior. But determine intercepts, asymptotes. Symmetry of the graph can sometimes help us. Then we'll look for the first and second derivatives. Look for your critical points. Look for your possible inflection points. Use them to determine your relative extrema, your points of inflection, your concavity. And then we can pretty much sketch things in. So that's pretty much the gist of this lesson. Now we're just going to work examples. So this one I have typed out the examples. If you're just looking at the slideshow on your own, do this with the animations. Don't just bring up the slide, because that brings up, bam, lots of information at once. We're going to slowly work through this one together. First, think about domain and range. We look right away and see x squared minus 4 in the denominator. So where that equals 0, x equals plus or minus 2. So my domain is x cannot equal a positive plus or minus 2. These are going to be my vertical asymptotes. For horizontal asymptotes, I'm going to look at the end behavior. Now I can look at this x squared. This is an even function, so it's going to have that even symmetry. So I know the limit to positive infinity is going to be the same as negative infinity. I don't have to worry about that. Factor out the 2 is always nice, not have to worry about that. I do our little trick of what we were doing last time, divide by the highest power. I'm going to get 2 times 1 or 2. Or if you use what you saw in pre-calculus, we said, oh, coefficient on the top is 2, bottom is 1. They're the same degree, so the end behavior is 2. This one works nicely on here. So we have vertical asymptotes at -2 and +2. We have a horizontal asymptote at 2. Sometimes I'm going to be putting things on this graph as we go through. Sometimes that works well. Sometimes it's hard to, you don't know maybe how to number the y-axis until you start finding where some of those other points are. So sometimes it's a little dangerous to do this. But generally your x is okay by the time you've got to this point. You can set that up. I look for the x-intercept. Where does the function equal 0? And again, fraction, I can ignore the denominator. Just look for where the numerator is 0. That's at plus or minus 3. So I have my 2 x-intercepts now on my graph. Y-intercept, I just plug in 0 for x. I get 9/2. So I got that point. So now I actually have some points on my graph I can deal with. Awesome. Now we go with our derivatives. So first derivative, we're going to have to use the quotient rule on this one. And our first derivative is going to end up being 20x. We'll go back up to here. 20x over x squared minus 4 quantity squared. So critical numbers are where that equals 0. And that's going to be where 20x equals 0. I mean, where the derivative does not exist are also critical numbers, but where the denominator doesn't, where the derivative does not exist, are also not in the domain. Those are those asymptotes. So that's why we don't consider those as critical values. They're not in the domain. Do the second derivative. We got the quotient rule again, blah, blah, blah. So again, where it doesn't exist are the points that aren't in the domain. So we look at where does the numerator not equal, or does the numerator equal 0? And you notice the numerator can't equal 0 because we got 3x squared plus 4. That's always going to be bigger than 4. So there are no inflection points. There are no places where it changes concavity on an interval. But again, you got to realize these asymptotes break us up into different intervals. So don't worry about inflection points. So our test intervals, if we get my little banner off the bottom there, is going to be here, negative infinity to -2, -2 to 2, and 2 to infinity. Those are the points we're going to check. Kind of nice, we already have a point in each one of these. We only have one critical value, and that's at 0. So this one, there are no critical points in this first interval. So I'm just going to look at, pick one point on that interval to check concavity. So I'm going to check at -4. You plug in -4 in here, or sorry, plug in -4 in the second derivative, you get -0.11. So that's concave down. We know it's concave down. we know it has to approach this asymptote and approach this asymptote. So it's going to be a curve like this. I have a point it goes through. I can kind of nail it down a little better. And this is as close as I really need. I don't need perfection on these sketches. My second test point interval, the -2 to 2. I have a critical point on there, so I'm going to check that point. I actually know what that point is because it's the y-intercept, 0, 4.5. Oh, sorry, that's my test point. I got to plug in the second derivative. I get 1.25. That means it's concave up. That means it's a relative minimum, so it's going to look like that. Third test interval, again, no critical points. So I just pick a point. I see again I'm concave down. I expect that because I said it's an even function, so it should have that even symmetry. There's my graph. If I plug this up with decimals, I get this. So again, I would say use your graphing program to check it. When you're trying to check something you drew with your graphing program, set the window up to pretty much equal the window here. You know, as here I went up to 8. I went from about -10 to 10. I go from -10 to 10. So that's pretty much what I set this graph up so that they look very similar. So, give this one a try. Pause the video. Take some time to work this. See what you can get on it. Then come back to the video and we will kind of talk through this one together. Do. So first thing I'm going to work with is, I can see right here x minus 2. So I have a vertical asymptote at x equals 2. My domain is x cannot equal 2 for this one. I'm going to look for end behavior, so I'm going to look what's the limit as x approaches infinity of x squared minus 2x plus 4 over x minus 2. And I'm just going to look at this and say numerator is second degree, denominator is first degree, so this is going to go to infinity. It can go over either to plus or minus infinity. So I got to think, well, as we're going, which way are we going? Because we know we're going to infinity. So if we're positive numbers, this x squared is going to take over, and it's going to be positive on top. But on infinity minus 2 is still positive, so it's going to be positive infinity on the right. But when we go to negative infinity, this is going to be a negative infinity minus 2, so this will be negative. The numerator is still going to be positive. So my limit's going to be as x approaches infinity, f of x is going to approach infinity. As x approaches negative infinity, f of x is going to approach negative infinity. So the limit does not exist. There's not a horizontal asymptote. So no horizontal. But it does have this end behavior. So that's what's going on there. I'm going to be kind of erasing stuff as I go along so that I have, let's make a bigger eraser here. I would rather graph on this background than on the graph background I have with this program. So next thing we're going to look for are intercepts. So for the x-intercepts, we need 0 equals x squared minus 2x plus 4. Because as long as x doesn't equal 2, this doesn't factor into anything. Well, if you look at this, doesn't factor quickly off the first bat. You first look at that. Factors of 4 that add up to a negative 2. Yeah, I don't like that. So I'm also going to say, well, okay, is it irrational or is it not real? So I'm going to think back to quadratic formula. Discriminant b squared minus 4ac is going to be a negative 2 squared minus 4 times 1 times 4 is a negative 12. And so that's negative less than 0. That's going to give me an imaginary roots. They're not going to be real, so there's no x-intercept. Y-intercept, we just go, what's f of 0? So that's going to be 0 squared minus 2 times 0 plus 4 over 0 minus 2 is 4 over 2, which is 2. So I have no x-intercepts and a y-intercept at 0, 2. No x-intercept. Y-intercept is 0, 2. Negative 2. So now let's go to fun with derivatives. If I go first derivative, x minus 2 times derivative x squared minus 2, or sorry, 2x minus 2, minus x squared minus 2x plus 4 times the derivative of x squared minus 2, which is 1, divided by x minus 2 squared. So there I'm going to get 2x squared minus 2x minus 2x plus 4 minus x squared plus 2x minus 4. So those cancel. Those cancel. That's going to cancel one of those. I'm going to get x squared minus 2x minus 2x. No, I messed up. 2 times 2 is 4. One of these is a 4. That's 4x over x minus 2 squared. So my first derivative is going to be x times x minus 4 over x minus 2 squared. Or I could write that as x squared minus 4. When I go to the second derivative, it might be easier to leave it that way. I'll maybe do it the other way. Back up. When I'm finding critical points, it's easier to factor it out that way. X squared minus 4x over x minus 2 squared. So I want to look at possible critical points. Again, when we look at this, where does it not exist? At the vertical asymptote, so I don't have to worry about that. I look, where does x squared minus 4x equal 0? That's where it's nice to say x times x minus 4 equals 0. So x equals 0 and x equals 4. And let's go ahead and find out what those points are. So at x equals 0, I already know what that is. Because x equals 0, y equals negative 2. I also want to say, well, what happens when x equals 4? So I plugged 4 in for x into here, and I get 6, I believe. I don't know. There I have 6. So these are my critical points. So I have critical points at 0, negative 2, and at 4, 6. And there's still more we got to do. Now let's go to our second derivative. So again, second derivative, I'm going to have to use my quotient rule. So I'll get x minus 2 squared times the derivative of the top, which is 2x minus 4, minus x squared minus 4x times the derivative of the bottom. Now, bottom, I'm going to need chain rule. So this is going to be 2 times x minus 2 times the derivative of x minus 2. And all of this is going to be over x minus 2 to the 4th power. Now, I do have a common x minus 2. So that can help me off right off the bat. Make things a little smaller as I go through here. So I'm going to get x minus 2 times 2x minus 4 is going to be 2x squared minus 4x minus 4x, not squared, negative 2 times 2x, okay, plus 8 minus 2x squared plus 8x over x minus 2 cubed. And again, I look, anything minus 4x minus 8x plus 8x, 2x squared minus 2x squared, all cancels out. So my second derivative of x is 8 over x minus 2 cubed. And this has no inflection points, because this can never equal 0. Where it doesn't exist, again, is not part of the domain, because x cannot equal 2. Okay, so let's start putting things together now. Let's see if I can make this work. So if I look here, I got my x has to go to up to 4 is one critical point. So let's just go this 5, 10, negative 5. I have critical points at 4, 6, and 0, negative 2. So I'm probably good with that. I know I have a vertical asymptote at x equals 2. So I'll sketch that one in here. I know I have a y-intercept at 0, -2. I know I have critical points at 0, -2, and at 4, 6. So, for my critical points, at 0, -2, I'm going to check concavity. So I'll try f double prime of 0. And second derivative at 0 is going to be 8 over a -2 cubed. So positive over negative is going to be less than 0. So this is going to be concave down. I know at this point this is a relative max. So this is going to have to come down here. And this is going to be going down to infinity. If I had figured out that flat asymptote, I could draw that a little clearer, but that's good enough there. When I look at my critical point at 4, 6, I look at the second derivative at 4. Again, 4 minus 2 is a positive 2. 2 cubed, that's going to be 1. That's going to be greater than 0. That's going to be concave up. So that's a relative min. So again, this has to be a lowest point, so this is going to go up. So it must go up to the asymptote, and this must kind of keep going like that. And there is our graph. Wasn't that fun? Okay, the rest of what I have on this slideshow are more examples for you to work. I will work on these, do these, put 2 examples on each video, so I'll make 2 more videos. So if you want to look at more examples, you can look at them there. Each one has different features that are worth looking at, but I don't know how much time you need to invest on this as you're working with this and working through this. Come back to these, that'll help you. You can look at your slideshow and say, hey, there is a problem, you know, which problems do you want to see me going through? But these are the problems I need you working on. You notice I only gave you 3 problems as homework because they take a lot of time. I would like you to try some of the examples also on the slideshow, but those I can work you through that, then try to do some on your own.